So, good morning everybody and welcome to NPTEL video course on design, verification and test of digital VLSI circuits. So, this is the first lecture of the course in which we will try to find out what is the goal of our course or what we are trying to achieve out of this course. So, just if you look at the key terms of this course, that is design, verification and test of digital VLSI circuits. So, what is a circuit? So, if you just look at the basic term, circuit means it is a device or an object which transforms electrical signals. You give one forms of signals and you get other forms of signals, okay, or in a very quote unquote formal terms, a circuit is nothing but it is a closed form where electrons can travel. Now, these are all your undergraduate stuff. Now, what is a digital circuit? So, in digital circuits our inputs and outputs are different voltage levels. We do not have any kind of continuous time current or continuous time voltages. If your circuit has continuous time currents and continuous time voltages, then it becomes an analog circuit. In case of digital circuits, we have discrete different voltage levels, and in most of the cases we have two voltage levels, that is 0 and 1. For 0 we say that is around near about 0 volts, and in case of logic 1 we say it is 5 volts in case of some technology, 3.3 volts in some technology. That is, we have discrete voltage levels. We all know that, then it is called a digital circuit. So, in this course we are going to see about design, that is, we are given a specification, you design a circuit. Like if I say that I want to build a 1-bit adder, so you know that sum is A dot B and carry is A or B kind of a thing. The sum is A or B and the carry is A dot B. So, it is very straightforward, that is from the design we make a circuit. Then what do you mean by verification? That is, you give some inputs to your circuit and then you check whether it performs as desired, right. In case of adder, so you know that sum is basically A plus B and carry is generated when both of them are 1, that is A dot B will generate your carry. So, you will just give all inputs like 0, 0, 0, 1, 1, 0 and 1, 1. So, you can say that you verify your circuit that finally it is giving the correct answers or not. And then test means what in this case? You design the circuit, then you fabricate it because you need to generate a circuit out of it which is hardware circuit. So, that is actually in this class is called VLSI because the technology is very large scale integration. So, when you are fabricating a circuit in very large scale technology, you finally get the hardware circuit out of it, and in case of VLSI we can put millions of transistors. So, simple adder is a very minute example of a circuit in terms of VLSI. We can have as a multiple core processors, as we are having quad cores or even 128 core processors. You have embedded stuff running on your mobile processors, you have so many hardware processing units in a car, all those things you are currently all listening about. So, our circuit these days are highly integrated, large number of transistors and millions of gates are integrated in one chip, that is actually called VLSI. So, in VLSI digital circuit, what do you mean? It means all the digital circuits where we have integrated millions of transistors to meet our specifications, and in this course we are going to see design, verification and test of those circuits. In case of testing, once the circuit is fabricated, you give some inputs, hardware inputs from the signals from a logical electrical signals and see if everything is operating fine or not. So, in this course basically you see we can think about this design, verification and test in two paradigms. You can think that given a specification as how I do a design as a simple adder I have told you, then how you do verify it is fine or not, that you try with all possible inputs and then see if it is okay or not. So, once it is verified to be okay, then you fabricate it and then get the final chip and then connect electrical signals and apply signals and see whether it is fine or not. So, that is actually called design, verification in test in one paradigm. But in another paradigm, if you think of the same problem, so as I told you, adder is a very simple example, or you can say that a minutest example of a circuit, very small circuit example is, but all practical VLSI circuits are very large or very complex in nature, like a processor, like you can say a graphics processor and so forth, which are doing large very complex application for us, like a Pentium processor or a processor which is running in which is processing your video game applications, processor which is processing your mobile applications. So, they are very complex in nature. So, if I say that you just do everything manually, that is from the specification you design a circuit, like in case of adder for the that is for the sum you do an OR gate, and for the addition and for the carry you generate a OR gate. So, it is a very simple design. You can do it by A dot B means you have an AND gate, A or B means you have an OR gate. So, you can do it manually and then you can test by applying some patterns, and then finally when the chip has arrived you put it in you have all done it in your undergraduate digital lab. You put the chips on a breadboard, connect it to the voltage supplies and see the results in the LED. But if it is a very complex circuit with having hundreds of inputs and millions of gates and having hundreds of outputs, then this cannot be done manually. It is extremely difficult to do all this stuff manually. So you require some kind of CAD tools which will help you, or which will automate the design for you. You give the specifications, then it will help you to generate the output as a final circuit, and then you find out mathematically, you can try to prove that whatever I have designed is mathematically obeying the what specifications I require, and finally there will be some kind of algorithms which will tell you what patterns to apply in the hardware level, so that you can know that your circuit is operating fine. In other words, the whole design flow starting from design, verification and test can be automated or helped using some automated tools. And if you are going for VLSI design, it is mandatory, or quote unquote it is very almost impossible to do without the help of tools. So there are two ways of looking at the problem. So in this course we are taking the second approach. So in this course we will not teach you explicitly how to design and how to verify or how to test a circuit. Rather what we will do is actually, you can call it the CAD for design, CAD for VLSI kind of a course. In this where we will try to teach you that given a specification, how you can write automatic tools or how can you develop algorithms which can automatically design the circuit for you, automatically verify the circuit for you. You given a circuit specification and an input specification, you give a circuit description and you give the input specification. Automatically some algorithms are to be developed, some automatic tools to be developed which can tell that whether the circuit is meeting the specification or not. Similarly for kind of testing, you have to tell which are the test patterns to be applied, because if you try to apply all possible test patterns, I mean testing may take millions of years, because in case if the circuit has n number of inputs, all possible combination is 2 to the power n. So everything is exponential in this world of VLSI. So what you have to do, you have to tell how automatic tools will tell you which are the minimum number of test patterns have to be applied to get a desired quality of desired quality of production. So we require CAD tools to help in all aspects of design in VLSI design. Okay. So this course will not, I mean again I am emphasizing the output, but the outcome of after you do this course, our goal is that we will be able to develop, or you will have learned how automatic tools are developed or how algorithms are developed which can automate design, verification and test flow in digital VLSI circuits. So in the first lecture what we are going to see, we will give an introduction to digital VLSI flow, that is what are the steps that are required to go for a digital VLSI design, and hand in hand we will also tell you why the process are a bit complex and how tools and what can be developed, or how once you know that these are the steps for VLSI design of digital design, then you can think that what are the tools required or what algorithms can be empowered or algorithms can be developed which can automate this. So we will take a very small example in this lecture and take you through the different steps of digital VLSI design, and then in the following and then the course will actually have 3 modules, one is for design, one is for verification and one is for test. So in that what we will do, you will go through all the different algorithms to automate different parts of this of the basic design flow, having 3 major parts: design, verification and test. So in the following lectures, today's first lecture is the introductory lecture, in which we will tell you the different steps in the flow. In the following using a very simple example, in the following lectures and the modules in the course, you will be learning about automatic algorithms which will automate the different parts in this. So I mean slowly we now move into the digital VLSI flow. So I mean we first see the introduction. So what is actually VLSI design? So now I mean we have all written C programs when we have given a functional requirements, like you have to add 10 numbers, or you have to do multiplication, you have to do array addition or something like that, finding arranging numbers in ascending order and so forth. So in all these cases we are very much well equipped to write C codes for that. So if you are asked to write a counter for a C code, so you can write for I equal to 1 to n, I equal to I plus 1, something like that, and you can implement up counter, down counters. Also we have also learned in basic VLSI, I mean digital design, digital design, which is a second year undergraduate course. So we have already seen that how the same thing can be done in case of a hardware, like you can connect some D flip flops, then you can go for a finite state machine minimization where the present state is 0, then the next state is 1, then again we have the first state as 1, then the next state is 0 and so forth. So you use Carnap map or what you can call Quinn-McCluskey method to minimize the circuit, and then we implement what you call circuit, which actually also works as same like the hardware. I mean which is the hardware, it works very similar nature as the software like the C program. So whatever we have learned in the undergraduate digital design is nothing but actually a miniature version or miniature part, or you can say a very small sub part of what is VLSI design. So like for example, if you think of a adder or a multiplier or a very simple like counter, they can also be called VLSI designs, but only it is actually not a very large scale integration. VLSI actually stands for very large scale integration, and in digital design actually we have seen the miniature versions or small scale integration level stuff we have seen. That is, the basic philosophy also remains the same, that you have some specification, that is like counting n numbers or adding n numbers, or like multiplying two vectors or something like that, or arranging numbers in ascending order and so forth. So, the specification remains more or less the same, but in case of hardware, one in case of the C language or Pascal or Visual Basic or whatever you use, they are all software based implementation. Now, the philosophy of VLSI or hardware is that the same algorithm or the same specification can also be implemented using a hardware. So, if you are using a hardware, it becomes a dedicated application and it runs much faster and all. So, all these the discussions in details, all these times, like how a specific application, how if you are making an application specific hardware, so it runs faster and all these things. Like for example, if you are in a C code, okay, so it works in it runs in your processor. So why do I again require to make a hardware block for that? Because your microprocessor in your computer can do almost everything. Then why do you require to make some specific hardware to do a specific part of your code? Processors are, that is why called general purpose processors. That is, whatever any specification you can give, it will implement, or it will have the implemented version for it. You can write it in any high level programming language. Then why do you require a hardware version for that? Actually, hardware version if you develop, so a counter will be a counter, it will not do anything else. So it will be actually application specific. So if it is application specific, it will consume much less power, it will be much faster and so forth. So if you require only to up count or down count or add some numbers or something, as a very special application which you want to put in your mobile phone or in your laptop or something, or some other app device, then why do you want to put a general purpose processor? Because general purpose processor is expensive, it takes more power and has several other disadvantages. So if you have some specific objective in mind or specific application in mind or very specific specifications in mind, it is always better that you go about designing a very specific or application specific hardware. So that is the advantage of application specific hardware. Throughout the course we will have much more detailed discussion, and we will explain why application specific hardware is more reliable, more advantageous compared to the general purpose processor for many of the applications. So, that is what is a very basic idea, that why do you want to go for hardware design of many algorithms. Hardware design of many algorithms are important because sometimes we do not require the general purpose capability of a processor. A processor can run any application, you just have to mention the software version in a program and it will do it for you. But many cases, like for example in a digital camera, you just want to do image processing, you do not want to do array multiplication, or maybe you do not want to do what you call some kind of printing purpose, and all these things may not be required in a camera. It is just required to some digital processing, taking the image from the lens and so forth. So if I have to connect a general purpose computer to a camera, it will be very bulky, heavy and power consuming. So we have to develop a very specific hardware which can do this only the required functionality for you. So for different specifications, we have to develop different ASICs, or which is called application specific integrated circuits or application specific processor, which will actually do only a sub part of the job for you at much lower cost and much lower power. So this is the motivation of motivation for VLSI designs, that whatever algorithm we have, we need not use a general purpose processor, rather you can make a simple hardware version for that and implement it as a separate IC and sell it in the market. So now what has happened in the last 10 years or about last 2 decades, the quality of integration, that is if you look around 30 to 40 years back, in a single IC you could hardly manufacture some 10 or 100 gates in the circuit. But with the large scale integration possible, or the very ultra large scale integration possible because of the advances in fabrication, we can put millions and millions of transistors in one chip. So that is why our Pentium chips have millions of transistors in one chip, and it can be done because of the highly sophisticated fabrication technology that is available. So what now we have achieved, the functionality of all our electronic equipments and gadgets have increased phenomenally, while their weight, size, power, everything has come up. This is because our fabrication technology allows millions of transistors in a single integrated chip, which is possible. So this integration facility has made us able to put millions of transistors, or you can say that system of systems, in a single IC, which is called system of chips or networks on chips. So you can put a large number of systems in a single chip, and which can be actually a system in itself. So that is what actually has helped us, so that almost all algorithms which were initially possible in a general purpose processor are now can be fabricated as a hardware, and they are sold off as specific processors. So if you say that is why I told you slowly we have moved to the level. So in about 30 to 40 years back, you can think that only tens of transistors were being able to fabricate in a chip, so it is called small scale integration. Then actually we have gone for hundreds of gates in one chip, so we call it medium scale integration. Now with about thousands of chips, if you can hundreds thousands of transistors you can put in one chip, we call it large scale integration, and above tens of thousands or lakhs of transistors if you can put in one chip, it is called very large scale integration. And nowadays a new coin is also termed which is called ultra large scale integration, in which you place millions and millions of millions of transistors in one chip and you get what you call the system on chips or network on chips. Are sophisticated versions, there are multi-core chips and all these things are coming up because of the ultra large scale integration. But generally you coin the term very large scale integration for both ultra large scale and very large scale, because that VLSI term is a more well accepted term these days. So that is what we have seen that. So because of the VLSI technology, that is putting multiple or millions and millions of transistors in one chip, has enabled us to fabricate system of chips or systems of systems on an electronic chip, making us capable of implementing any kind of software as a hardware function. And when you can make a hardware version of a software, it will be faster, low power, you do not require a general purpose computer, and there are many other advantages which we will slowly show in this. So what next we are going to see is that, so now as I have already told you, so that as this complexity issue, that is this VLSI circuits, as we told you, we are now fabricating around tens of thousands of transistors in one chip. So if you are designing you are making some design, it is impossible for a person to do that manually. How can you, where I have to put the 100 transistors, what will be the output, how do you connect it to the input of another block and so forth. So that is not even, that is impossible to be done manually. So we have a large amount of CAD tools which will actually do that for you. So we have developed, so this VLSI industry have actually two trends, two you can say two basic disciplines. One set of people are towards, you can think of broadly very in broad sense two disciplines. One is the design people will design, will take the specification, do the design, and they will see about how it is fabricated, how it can be tested, and how it can be sold to the market and all that. Another part of the people are software people who generate or who develop these CAD tools which can allow you to go for a very good VLSI design, because if you see that if millions of transistors can be possible in a chip, so the design complexity is very high. So it is impossible for a person to manually find out for a given application how will be the transistor level diagram will be and how it will be laid out in a chip so that it can be fabricated and all. So one set of people work for CAD, that is called VLSI CAD for design, CAD tools for VLSI is another set of discipline where we learn to develop CAD tools, and another set of discipline actually are take care of given a digital specifications or any specification, they want to develop what looks as a very good kind of a very good optimized design and fabricate it and send it to the market. So in this course mainly we will be looking into the CAD aspect, that how can we develop, being this course from computer science and engineering department of mainly focused towards computer science people. So our main goal will not be in the design part, maybe our idea will be to give you good CAD tools or develop good CAD tools so that they can aid the designers, so that they can get very optimized or they can be able to generate optimal designs. So that is why, because the complexity, automated CAD tools are very much required. So this is actually called the design part. So when we say the design, verification and test in this course, here design does not directly imply that we are going to design some VLSI chips given a specification. Our idea here is that given a specification, how can you write good algorithms or good CAD tools so that you can automatically go for the design, or which can help the designer to go about making the design. So it is actually CAD for design. Design tools. It is the computer aided tools for design phase of VLSI design. In design phase we are not going to design any circuit, but rather we are going to develop CAD tools which can help the designer to design the circuit. So again, what is the idea is that, so say for example, even with the tools and all, some designer is designing the circuit. But again, as this thing is so complex that always some error might come into picture, like the CAD tools may have error, the designer might have made some error, and actually something we should point out that VLSI designers are hardware. So once you fabricate the hardware, it is sold to the market that you cannot debug. Like in a program, it is unlike a program philosophy. So when you write a program, then you distribute it to the customers, then you get lot of warnings and errors which comes back to you. You can patch up your code and you can again sell it to give it back to the customers. So once you give it back to the customers, then it is very good. Actually they can use that. So again they will report you the bugs. Again you are correcting the bugs, and again you are giving it to them. So this hand in hand finding of bugs and solving the bugs or patching the bugs is always possible in the software industry. That is actually a very good sign, very good aspect of softwares, software programs. But in case of hardware, once the design is done, it's fabricated and sold to the market, it becomes a hardware component and it cannot be changed. If anything goes wrong, you have to throw it out and you have to put a new chip. So that is why there is no question of any debug after the design is fabricated. So before fabrication of the chip, when you are at the design stage, so we should be very careful that there is no error. So therefore we have something called formal verification step, that is in this case what we do. So, given a design, so if the chip has say n inputs, so if you try to exercise all possible input patterns, so the number will be 2 to the power n, and which may be a very large, like if you have a 100 pin chip, so your number of patterns to be applied will be 2 to the power n, all possible cases to find that there is no error. But that amount of testing can never, or verification cannot be done by any physical human, any human being in a physical, in a logical amount of time. So, that is what we do, we actually go for formal verification. There is a we make mathematical models of the circuit, and then we try to prove mathematically that the circuit actually obeys the specification, or there is no bugs in the design, or whatever you intended, that is you have designed. That is how, that is checking of the design intent, that is whatever you intended to design, that you have designed. So, all this we require, because in hardware if you make a mistake in the design, then it is fabricated, then there is no question of tracking back, because everything has been fabricated, you have to throw them up, there is no question of debug. So, whatever you have to do, all the debugs you have to do before you are sending it to the fabrication stage, before manufacturing. So, and therefore, there is a very important stage, the second step is called the verification, that given a design, how can you verify it? Again in this course, as I told you before, is not for taking a, it will not show you that you take a design and verify it. Rather than what we will do, we will see how tools can be developed, or how can you develop CAD tools that will help a designer to verify his circuit. So, in the design phase we will see how you can develop good CAD tools, so that he can design, I mean, in the circuits in a very easy manner, or he can help it. In the second stage, that is called the verification part of the course, we will tell you how verification tools can be developed, which can help a programmer, I mean, which can help a circuit developer to verify his designs, that whether they meet their design intent. And finally, a phase is called testing. So, whenever again as millions and millions of transistors are put in the circuit, so again the manufacturing process also is not very reliable. So, what happens is that you manufacture say 1 million chips, and you are putting more and more chips, more and more transistors in one chip. So, what may happen is that we will elaborate all this in the, all this stuff which I am telling now, we will be elaborating all this when you are going to individual modules. So, at the first lecture it will look more like a story rather than the very inside depth. So, just I mean take the words which I am saying, that when you are fabricating millions and millions of transistors in one chip, the manufacture stage is not very reliable. So, why is it not very reliable and all? So, that things we will discuss when we will be going to the individual modules of the course. So, as you are putting millions of transistors in one chip, so fabrication process is not even reliable. Even if your design was perfect, you have verified it to be functionally proper, then you fabricate it. In the fabrication stage, because of the millions of packing millions and millions of transistors in one chip, it may happen that there are kind of some manufacturing defect that remains in the chip. Now that is why you have to test each and every chip before you sell it to the market. Again, if you have n number of input pins to the chip, so you have to apply 2 to the power n physical vectors. So, there is a difference between verification and test. So, in verification what you do, your design is not at a hardware level, it is only at a software level. You have written some kind of a code like Verilog and all, we will see. I mean, we do not directly go on for designing a circuit by taking chips and putting resistors and transistors, we do not do that. We write this, our design in some high level language like C. In case of software, there is some language called Verilog and VHDL. By using those languages, you can develop your circuit in a software level first, and then you can do verification in the software level itself. That is, if the circuit is fabricated, whether there can be any defects or whether there can be any design bugs in the circuit. So, before manufacturing, your circuit is still at a software level, but which has to be implemented. So, what verification does, verification stage is also checking the software version of your circuit, that if there is any design errors or design intent is not matching in the design. So, that will be told you by the verification part of your verification CAD tools. Now, once you are verified your design at the software level, then you know that my design does not have any problem because it has been verified properly. Again, so you can sell it, I mean you can send it for manufacturing. But here also, if there are any inputs in the circuit, so if you want to verify it using software, because now your design is at a software level, at a program level itself, so it will take order of 2 to the power n amount of time. Now, testing is a much more complex procedure, because now your software design has now been manufactured or translated into a hardware. So, there will be say 10,000 chips which has to be sold in the market. In case of verification, your software, your design was a single program, so you have verified a single program that it is functionally proper. But now when you make a hardware version for that, you just fabricate it, there will be 10,000 chips which has to be sold in the market, and any of them may have a physical defect. So, testing you have to repeat for all the 10,000 chips. In other words, for verification there is a single code which you have to verify, but for testing you have to test all the chips that has been manufactured, because the problem can develop, because testing looks for problems that can develop in the manufacturing stage, because a chip is not sent to the manufacturing stage stage if it is not verified. So, a chip is sent to the verification, chip which is sent for the manufacturing or fabrication process, you can be sure that it does not have any kind of a design intent or design error. So, where from the error comes after fabrication? It is at the fabrication stage that there can be some kind of a defect that comes because you are putting so many transistors in a chip. So, fabrication procedure also may not be a very proper one. So, testing actually tests that whether even if the design was proper, the circuit may not work because there can be some amount of the manufacturing defects that has crept in at the at the fabrication stage. So, for testing purpose, what you have to do, you have to test all the chips which have been fabricated. So, if a chip has n number of inputs, so the order of complexity will be 2 to the power n into 1000 or 10,000 chips that has to be tested. So, testing will take even some more amount of time than verification. So, again what we have to do, we have to think how can we, and so if you think we cannot apply all 2 to the power n test vectors. So, we have to think which are the best some subset of 10,000, if the n number of pins in the circuit. So, 2 to the power n test vectors has to be applied. So, you have to think which is the best subset of 2 to the power n which you should apply to test your circuit, so that you can somewhat be confident that your circuit does not have any manufacturing defect. Let me tell you in the other way. So, what our course will do? Our course will not, in the testing part of the course, will not tell you how to, how a task circuit is being tested. Our course is not like you make a design, like you make a FFT processor, then how you verify your FFT processor and then how you test your FFT processor. That is, our course will not be like that. We will not take a single design or a set of designs and see how it works. Rather, we will tell you how CAD tools can be developed so that any design you make, it can help you. So, first we will see the CAD tools for design, next we will show the CAD tools for verification. In the test part of the module of the course, so what we will see? We will see how CAD tools can be developed which can tell you which are the best patterns to test your circuit. So, ideally speaking, you should be able to apply all 2 to the power n test patterns, then your job is done. But as the complexity will be very high, you cannot do that. So, what we will do is that we will try to tell you which is the best subset of 2 to the power n test vectors which can apply, then you can be very much confident that your circuit is 99.9% sure that there is no defect in the manufacturing stage. So, again we will tell you CAD tools for test. So, our circuit will have design, verification and test of digital circuits at the CAD tool level, that how can you develop CAD tools so that these processes can be automated and ease. So, we are always saying digital design. So, other than digital design, what are the other types of circuits available? So, circuits can be basically VLSI circuits can be divided into analog, digital and mixed signal circuits. Mixed signal means both analog and design. So, what is digital circuit? Digital ICs contain logic gates, flip flops, that is our basic whatever components we have learnt in our basic undergraduate VLSI the digital design course, all those you will have, and here signals are only logic 0 and logic 1 and you do binary operations on them. But in case of analog circuits, like we have seen current mirrors, voltage followers, op amps, filters, etc. They are the components which you have learnt in undergraduate analog electronics classes, and they work by processing continuous signal. Like in case of analog circuit, we have sine waves, we have cos waves, we have ramps, we do not have discrete 0 and 1s. And analog circuits and mixed signal circuits are something where both analog and digital components are like ADC, buck converter, etc. So, in our course, we will be only looking at the digital design part of the course, because it is said that digital designs are very complex, millions of transistors are there, designs are very complex, so you require a CAD tool support for that. It is indispensable that you cannot make any practical VLSI design without a CAD tool. But in case of analog design, we also require some CAD tools, but compared to digital design, the support is required is bit less, because in case of analog design, the circuit sizes are small and generally people design by hand. So, it is more like analog design, people call it as more like an art. So, you have to do good VLSI analog design, so you can lay out the transistors, laying out, the design of your gate, sizing of your transistors, etc. in analog, everything is done manually and as of now. But only you want to verify, because there is some simulations, CAD tools are basically simulation stages in there. So, you design some circuit manually and then you see by simulating the circuit that if I give these inputs, whatever is the outputs that you are getting, whether they are matching my specification or not. And in case of analog circuit, unlike digital circuit, the input and output specs are not very large. So, you can give a reasonably good subset of the all possible input cases and verify them at the output by manual comparison or some kind of preliminary comparison tools. So, therefore, analog CAD is basically based on simulation, which will take some inputs and show the output, and you can yourself verify whether it matches all the specification. But in case of digital design, the complexities are exponential, because if there is 100 pins in the circuit, the complexity of most of the steps will be order of 2 to the power n, which is infeasible to do manually. So, therefore, CAD tool support is very much required for digital design. So, in this course, we will be mainly talking about digital designs and CAD tools for design, verification and test. So, whenever you use the terms design, VLSI design in the course, so it will be only for digital design, and whenever we say design, verification and test, any of the coins we term, so they will be generally for
what? They will be generally for CAD tools to support this test. So, we are not going to see any kind of a specific design. So, that is what we are saying, henceforth in the course whenever we use the terms, they will be for design, digital design, and will be actually CAD tools for this one. So, in this video course we will be looking at the CAD tools for design, verification and test phase of digital VLSI ICs. So, today as I told you in the first class we are not going to look into what you called details of each of the steps, rather what will or rather we will not take a single step and go into details, that will be doing from the next class onwards. But from the first class what we are going to do, we will tell you what are the basic with a very simple example we will cover up all the possible steps, all the stages possible, all the stages that are taken, they are handled, or in other words we will take a very simple example and we will cover out all the phases which are followed in our digital VLSI design procedure. So, let us see, this is the first part of the digital VLSI design. So, first we have specifications. So, it is a manual level of specification, like you can say that A plus B equal to out 1 and C plus D is equal to out 2. So, this can be a very simple, we can say that all these things are single bit numbers O1 and O2 are to sum and carry bit numbers, something like that. So, these are our design specification. So, that is done manually. Next what we do is that then we go for a architectural specification called high level synthesis. Like in this case we will take an elaborate example. So, we will elaborate this example in the following slides. So, architecture example means you will take two adders. So, A, B, C, D, these are the two outputs. So, this is actually at a very broad level. Now, now what is the what else actually do in the architecture level? So, it is a very broad level. Now, the question answers that this is say operation 1, this is operation 2. So, we require two adders for that. Then actually you have to answer the questions like whether this adder will allocate to this one and this one to this one or vice versa. Sometimes we can also say that two adders are not available, single adder will be there. So, first it will do it for you, then the second operation will be done for you. So, when you are talking at the very broad level, at the architectural level, that how we can meet the specifications, so that is actually called the high level synthesis, which actually comprises scheduling, allocation and binding. So, scheduling, allocation and binding will elaborate shortly. So, basic idea is that we are making a block level diagram of a specification to satisfy a specification, and we are answering questions like how many adders are there, how many multipliers are there, which operands will go to which operator and so forth. So, once that is done, so we go for the RTL design and logic synthesis. So, what do you mean by RTL design? That is actually register transfer level design. So, in this case, so we saying that adder, then we say that registers, then we say that multipliers, then we set a clock. Then that in the RTL design what we will do? What type of adder do you want to use? Do you want to use a triple carry adder? Do you want to use a carry save ahead adder? Do you want to carry look ahead adder? Those things we decide. Also we decide registers. Do you want to use a D flip flop type register? Do you want to use a JK type flip flop register? So, what will be clock? Clock will be gated. So, many other register transfer level, but that is actually what the RTL means, register transfer level, that is we take decisions about the registers and the block level like adders, multipliers, subtractor, what type of stuff you want to use and so forth. And then we go for logic synthesis. So, what do you mean by logic synthesis? From the RTL level, now we have to go to gate level implementation. If you are taking a ripple carry adder, so there will be different gate implementation. If you want to carry look ahead adder, the gate level implementation will be different and so forth. So, in RTL logic synthesis what we do, we take the RTL level, like for example flop, we have to convert it into gate level. If you have an adder, we have to convert it into a gate level. Adder in the RTL level equal to A equal to B plus C. But now when we want to go to the RTL level, A plus B will be equal to A dot B and will be sum, and A XOR B will be the carry. So, we are going at the gate level. So, logic synthesis actually converts it into the gate level. So, now once everything has been done at the gate level, now your circuit has to be fabricated and sent to the market kind of a thing. So, what do we do that? We go for a physical layout. That is, once the gate levels are there, so actually this is the gate level kind of, the designs are there. So, actually also what do you call this, the VLSI circuit or the chip generally is not, in the chip you do not have, you never have gates like this. These are only for your pictorial view. Gates in a circuit are basically nothing but some rectangular like chips. So, we are not in this course not covering any kind of physical design. So, you can take any standard material and look about the physical design, but only to give you an idea that what is what. So, gate does not look like this. Gates are basically rectangle blocks, okay, and your chip is not actually, maybe your die of the circuit die will look something like this. It is a rectangular square in shape and it has some rows, okay. So, whatever gate you require, because gates in physically gates are actually some rectangular blocks different in width. So, you say this corresponds to gate 1, then this will correspond to gate 2, okay, and then maybe some other gates are there. So, it will be gate 3, this will be gate 4, okay. So, in physical design what you do, so you know that this gate is connected, all the connectivity and all the gates are available from the logic synthesis. It will tell you which gates has to be used, how it has to be connected, and all those information are given in the logic synthesis stage. Now, you have to put these gates and the interconnections in a block in a I mean what you can call a rectangle or a square, where there are some rows and the gates look like some rectangular blocks. So, your job is to how can you optimally put these blocks or these gates in this what you can call this die, this is called the chip. So, how can you put the gates, where we will place the gates, so that all the gates can be placed in a minimum amount of area. This is like a bin packing problem kind of a thing. So, you have a big box and you have different size of oranges. So, which oranges, how will you arrange the oranges in the box, so that the maximum oranges can be placed in this one. Same thing like here. So, there are some rows and your some gate will be this thick, maybe your OR gate will be this one, XOR gate will be longer and inverter will be thinner. Generally with this width, I mean the height is same, only the width varies in a very broad spectrum. So, very broadly speaking. So, if the gate takes more area, it will be long in this direction. This one we want to keep fixed, because this I mean we got width and the width of each row in the die remains same, so that you can place them accordingly. And then what you have to do, so you have to find out that how can, because different width, different length gates are there, you can think. So, how or different length blocks are available. So, how you can place these blocks here, so that the maximum number of blocks can be fitted over here, or you can take minimum area. So, again is a very interesting computational problem, how to do that. So, CAD tools are available which can also help you in doing this physical layout. So, once this gate level connectivity information is given by logic synthesis, in the physical layout what we do, we place these gates in the die in this way and do the interconnection, because again if this point has to be connected to this point, you have to route this, and again if this point is connected, you have to route this without any kind of shorts and all those things. So, what the physical layout will do, physical layout procedure will put all the gates in the die, so that the minimum area is taken, and it will also route the input, route the pins, route the connections in the gates. So, that is actually done in the physical design. Again, obviously if you are having millions of transistors, so millions of about lakhs of or thousands of gates has to be put in the circuit, or transistors has to be put in the die, and again interconnection has to be done in between them. This is like a graph of about 1 million nodes, and you have to connect one node of the graph from the other. Again, that is a very, very computationally tough problem, and you cannot never do it manually. So, there are CAD tools which can help you in the physical design process. Okay, and at each step, as you, so this is basically the first few steps. Next few steps will be shown in the next slide. So, these are the first few steps of digital VLSI design, and at each partition dotted line you can see that you are saying verification of RTL with specs, verification of logic synthesis with RTL design, verification of circuit extracted from layout with logic circuit. So, what does this verification imply? That means at this level your design was at some logic or some manual or some specs level or RTL level, architectural level. From here what you have done, so you have got a RTL design from that. So, here it was at the block level, or it was at the architectural level. From here you have come to what you call the RTL level. So, now there is some translation. So, you have to see that whether the translations are valid or they are equivalent or not. So, we require a verification here. Like here we have the logic synthesis, that means now you have a gate level, and what you get over at the physical layout, everything has been laid out as a circuit and interconnection has been done. So, now again also you have to find out whether this translation was equivalent or not. If the translations are non-equivalent preserving, then there is deviation in the design, because you have designed something here, it has changed in the next stage and you may not be able to meet the specification. So, at every stage when you are going from one form of design to the other, like initially it was specs, then you have go to RTL, you have to high level design, then it is RTL, then gate and then layout. So, same design or same specification, you are converting it into different types. So, when you are converting from one type to another, you have to verify that they preserve equivalence. If somewhere it gets changed, then there is a problem. So, once all these things are done, so before sending it to the market, we also go for a test planning. That is, given the circuit, because we already have the software version of the circuit and it has gone to the market for fabrication. Meantime, what we can do, you can find out, because if there are n pins in the circuit, you have to apply 2 to the power n vectors to test it, which is very much impossible. So, you have to find out a subset of test vectors which you can apply, and then you can be relatively very confident there is no defect in the circuit. So, the subset, like L is the subset equal to 2 to the power n. So, that subset has to be found out. That is actually called test planning. So, given the software part of the circuit itself, because it has gone to fabricate, you do not have the fabricated stuff now, it is not also required for test planning. So, looking at the gate level diagram, looking at the layout, how you are planning to put this stuff in the die and all those things. So, our software version will always be available to you. So, by looking at that, you should be able to find out which are the best 2 to the power, best subsets of 2 to the power n vectors which you can apply, and you can be reasonably very happy that your circuit and circuit will be what you call your circuit will be able to be tested with the subset, and you can be relatively very confident the circuit does not have any manufacturing defects. So, this is actually called test planning. So, once the test planning is done, so you can also say that after that we can go for fabrication, but in a very general, I mean very broadly speaking, we can also say that test planning can go in one hand, and you can go for the fabrication and manufacturing fabrication in another stage, because once the chip is designed, so you can send off it to the market for manufacturing, send it to the vendor for manufacturing, and meantime you can find out your test plan. Now, once you have your circuits ready, so after fabrication you will get your circuits, so that you have to test using these test patterns, and whatever chips you find that do not have any effect, you give it to the customers, and faulty chips you can throw off to the market, because we will see in the end of the course on the testing module that repairing is not a very essential part of VLSI testing. So, we will see that. So, that is what is the basically the design verification and test flow for digital designs. Now, what we will be studying in this course, again repeating. So, we will be looking at the CAD tools which can help you in all the phases of the design. For this phase, we will have some high level synthesis design tools, what you call CAD tools we will see. In this phase, we will see logic synthesis tool. So, this part I think many of you have already learned, like Karnaugh map and Quinn-McCleskey. They basically take your design and you are generate like counter, adder and all those things, and you generate the gate level design. So, I mean Karnaugh map and what you call Quinn-McCleskey can work up to 10 variables or 20 variables, but in VLSI we have 100 variable or 1000 variables even. So, how can you do a Karnaugh map type optimization for 1000 variables? So, you require different types of CAD tools for that. That we will be learning in the second phase. Third phase also, so given a die like this and an interconnection of gates. So, how can you put the gates in different rows, so that minimum area is taken and everything can be connected. So, you require CAD tools for that. So, this is actually called back end part of design. So, and we are in this course we will not be looking into this part of back end part of your digital design, because we are covering some basically the front end aspects of the design. So, in VLSI there is something called front end and something called back end. Front end means it is design, verification and test plan development, and back end means how you are going for layout, routing and fabrication, that part. So, as we are merging three broad courses in one small, basically we have separate tools, separate courses for VLSI design, verification, test and back end. So, in this course we are trying to give you a brief overview of the front end part of VLSI design flow. So, what we are going to do is that we will be telling you mainly about design, verification and test flow and what CAD tools, how CAD tools can be manufactured for, CAD tools can be developed for them. We will not be covering the manufacturing stage, manufacturing process, as well as we will not be covering details about the physical layout, how physical layout is done, how CAD tools can be developed, that we will not do, because for verification, for test, for manufacturing, for verification, whatever modules we will be studying over here. So, there can be separate full fledged semester courses run for these courses, but the aim of this course is that if you want to understand in a nutshell how digital design is done or what are the CAD tools for digital design. So, we have developed a course which can give you a flavor of all the parts of the front end part, that is design, verification and test. So, as we are covering 3 modules in 3 broad courses into one course, so it will be a heavy load, or it will not be proper to include one more module, that is the back end part in this same course. So, we will be covering mainly the front end design CAD tools. Okay. So, now whatever we have told you, so we said that we will be illustrating you using an example. So, okay, so what is the specification? So, let this be the production specification. So, out 1 equal to A plus B, out 2 equal to C plus D. A, B, C, D are single bit inputs, out 2 and out are 2 bit outputs or sum and carry. So, we want to do that. So, let this be the specification. So, how you go about it? So, first is called the high level synthesis. That is what I told you, that you have to design at the block level. So, what is high level synthesis? High level synthesis algorithms are used to convert specifications into RTL or high level circuits. That is like adder and all those things. At a very, even it may be much more higher at the RTL level. We generally call it as RTL level. A high level synthesis actually converts specifications to, you can say, black box type of levels like adder, subtractor, registers and something like up counter, down counters, some registers, and so you can call it, it's a very near to RTL design. RTL means register transfer level, that is you have in between 2 registers how data will be flowing, that functionality will come. So, we will solve using examples. So, that is why sometimes RTL high level synthesis is called as the architectural synthesis. That is, we just say in blocks, adder, multiplier, divider, registers, interconnections in between them and so forth. That is why actually it is called the architectural synthesis. So, high level synthesis basically sometimes called architectural synthesis an automated design procedure, because we will be developing CAD tools. So, high level synthesis tools, what it will do, they are actually nothing but automated design tools that will take a specification, algorithmic description, and it will convert it into an RTL or a architectural design. So, that is what we are going to see as high level synthesis CAD tools. Basically, high level synthesis means taking a specification and converting into something like a architectural design, or what you call a near about RTL design. That is what is the high level synthesis. Now, here we will, in this module we will learn about tools, CAD tools which can automate that. So, how do you, so how do you write your intent? We generally, in this case we have written our intent in like this one, but generally it is written using some kind of languages which are called System C, Verilog, or some other language. We will not be going into depth in these languages, but whenever required we will give connections to that one. So, basically we write in some kind of a high level language, we write them all in some kind of a high level languages, like it is not C like System C, System Verilog. So, it is very easy to write hardware specifications in this. So, what this high level synthesis tool will do, it will finally generate RTL design, or it will generate what do I say, architectural block diagram. So, first what it does, it will first have to schedule the computations at different steps. We will see what do you mean by scheduling. Say if you have to add say A plus B and C plus D, these are two adders. So, there are two operations you have to do. So, you can schedule both of them in one step, or what you can do is that you can schedule A plus B in first stage and B plus C in second stage. So, this is actually called scheduling. So, what operations you will schedule in what step, that is called scheduling. And secondly, what you have to do, you have to use hardware. Like if I have two adders, then you can do A plus 1, A plus B and C plus D parallelly. But if I have one adder, then in the first stage I have to go for A plus B or C plus D, and in the second stage you have to go A plus B, or in the other way around, in first stage you do A plus B and in the second stage you go for C plus D. So, that is why you have to allocate which operations you do when, and that is you have to allocate your operations in different time stages, or what you can, different hardware, because it is only if there is single hardware, in the single adder, then A plus B and C plus D will have to be done in the same adder. So, here allocation does not mean anything. But if I have two adders, then A plus B will be in one block and C plus D will be in another adder. So, adder 1 will you do A plus B, or in adder 2 you will do C plus D, or vice versa. So, in which hardware you will do which operations, so that is actually called allocation and binding. So, here what we do, based on the availability of the hardware units and time, scheduling computations, what do you call are scheduled computations, because we have already scheduled our operations in time step 1, 2, 3. Scheduled computations are allocated and binded to the hardwares. So, that is actually called binding, allocation and binding. So, we will see with an example, then it will be made more clear. So, this is you see, this is our specification, that A plus B equal to this and C plus B. So, here we have scheduled. So, what is the scheduling over here? It is scheduled that both A plus B and C plus D are done in the one control step. So, this is one kind of scheduling. You can also have another kind of scheduling here, like you may not have it here. You can also have this one in the second step, C plus D and output. This also you can do. This is another type of a scheduling. But let us say that if you have some other specification like F equal to A plus B plus C, then you cannot schedule A plus B plus C in one time frame. It is impossible, because first you have to do A plus B, you get some output. In the second stage you have to use this and then C, and then you will get F. So, for this specification, obviously you require two time stages for scheduling, but here you can have flexibility, like we can schedule this here and the next block you can schedule here, or you can schedule this here and you can keep scheduled it here. So, scheduling actually it means that which operations you want to do in which time stages. So, sometimes like in this example like A plus B plus C, in this case you cannot schedule anything in one stage, you minimum require two time stages for this, but you can schedule this plus this in one stage, or B plus C in first stage, and with the temporary result you can add A in the second stage, or in the other way around you can add A plus B in the first stage, and in the second stage C you can use the temporary variable on this scheduling. Now, actually what do you mean by allocation and binding? So, let us see this. So, in this case we will take a different example. If you want to go for scheduling and scheduling, we have done allocation and binding. If you want to go for that, then it is very simple. Just if you have two adders, then you can just do it A, B, and this is C and D. And these are the outputs. Now, what is allocation and binding? So, in this one you have allocated A and B, and in this one you have done C plus D. Now, you can also the other way around, you can take C plus D in adder 1 and A plus B in adder 2. So, here we have binded A plus B to 1 and C plus D to 2, and you can do it other way. So, if you are directly mapping your scheduled operations to the hardware, so this by allocation and binding are very trivial. But now, if you think that I have only one adder, then it is a problem. Then actually what you have to do, so you have to schedule this one here and you have to schedule this one here. So, in this case, in the same adder what is happening? You are allocating both A plus B and C plus D. So, what you have done? You have allocated A plus B and C plus D to the same adder, because they are obviously same adder, but now here you have to depend on the time step, whether you want to do A plus B 1 over here, and in the second time step you want to do C plus D, or the vice versa. So, depending on the hardware resources and constraint, schedule operators are allocated and binded. In this case, there is only one hardware, one adder. So, you can allocate, you have to allocate A plus B and C plus D to one adder only. So, you see they have been same adder they have used, and obviously the numbers are actually stored in registers. You cannot directly bring them numbers directly to the hardware multiplier or adder or subtractor. So, generally whatever way, when we are talking about variables in hardware, we store them in register. So, in this case there are 2 registers only. So, one thing I have to mention, that not only what you call adders or multipliers or subtractors can help you out. So, you also have to have registers to store them. So, in this case you assume that there are 4 variables, but we assume that there are only 2 registers. So, first you do this, and then the same registers and adder you use for C plus D. But if you are taking this type of a case, then also you have to have 4 registers to do this, because wherever you have variables you do this. So, again you can think that for R1 I have allocated RA1A, for R2 B, R3 C and R4 D. So, there can also be interchanges in between them. So, actually this is called allocation and binding. So, variables are allocated and operations are allocated to hardware. So, so that is what I have told you. So, in the running example there are 2 operations that we are doing in 2 control step, that is 2 control step, because we have only 1 register, 2 registers and 1 adder. So, first one you do this, second one you do this. So, this is what has been told. Okay, now what I was talking, so if you have straightforward 2 adders and 4 registers, so there is no question of any kind of scheduling, everything is scheduled in the first stage, only you have to decide in which adder you want to do A plus B and which you want to do C plus D, and similarly for the registers which variable you want to allocate and bind where. So, that is what, so what is the idea? In case of scheduling, you schedule which operation has to be done in which time step, and in allocation and binding, given different hardware, so in which hardware you bind which variable and which operation. So, that is actually called allocation and binding. So, in high level synthesis, what we do, the 3 steps, we schedule, allocate and bind. So, at the end we get, what do you get? You get a circuit like this, or you get a architectural design like this. So, you get an architectural design like this. So, that is the output of high level synthesis stage. So, in this slide they are saying that if you have 2 adders for force multipliers, then now we will see, so it says that, in this case it says that, allocation times scheduling is in single step, allocation binding can be done, in adder 1 you can have A plus B and C, or you can translate them and all. But now there is one very important thing. So, in this case you see this is very good, it is a very good looking stuff, but it actually everything is done in single stage, but you can think that, see here that there is a problem, we require more hardware here than here. In this case we require only 2 registers and 1 adder. In this case you require 2 adders and 4 registers. So, a person may not be happy with this. This is very fast, because in one stage you will get the answer, here you require 2 stages, but still somebody may say that I do not require a very fast operation, then I do not want to go for this design. I always want to go for this design because I do not need a very fast operation. But there is a big but over here. So, in this case there is no control, you directly A comes, B comes, C comes and D comes. But if you want to do this in a single adder and 2 registers, then there is a problem, you require a control circuit for that. So, what is the control circuit here? You see, first A will go, then B will go, then the same register C will go and D will go. So, you have to have a multiplexer, and initially the control will be 0. So, A will go, B will go, and in the second stage control will be made 1. So, in that case C will go and D will go. So, here you require a control circuit which will first generate 1 and then generate 0, and first generate 0, so that A will go here and B will go here through the mux, and then 1, so that C will go here and D will go here. So, you require a control circuit for that. So, even if you are saying that I do not require a very fast operation, so I can use single adder and 2 registers and 2 registers. So, this is what I want to do, but you require a control circuit and you require some multiplexers. So, nothing comes at free. So, even if you want to go for a very fast design, fine, you take a very big circuit here and you do not require any kind of a controller over there, because it is very straightforward control is there, because there is nothing to multiplex. But if you are going to go for a minimum design here, minimum hardware design there, so you require a control circuit, and it will also take some area. So, obviously the area of the controller will not be as large as this one, but some penalty you have to pay, that is what I am saying. So, high level synthesis not only goes for allocation scheduling, allocation and binding, but also it will tell you how the controller will behave. Because if you are going for this small structure with 2 multiplexers, 2 registers and 1 adder, then you also require a controller. So, high level synthesis will also tell you how the controller will behave. So, that is what this is what is being saying. So, if allocation and binding is according to 2 registers, 4 registers, the control is trivial, but if you are using the small structure, so first stage A and B should be fed and second stage C and D should be fed and so forth. So, you require a control circuit for that. So, this is how what is your high level synthesis has done. So, next what is the case? So, from the high level synthesis you have got this structure as well as this controller. So, in logic synthesis what you do? You have to convert this actually you can also call as RTL level or architecture level, you have to convert it into gate level. Okay, so, how do you do that? So, it is a way, this is already we have already done it in our digital design class, that if you are given, so here you require how many blocks? So, you require registers, multiplexers and adders. So, here we will give you the example of a adder. So, how do you do that? That is very straightforward. Sorry, I will just show you how you do that, then you will come back. So, in this case you see we write the truth table of an adder. Okay, so, it is A, B, this is out and sum, and then we can easily go for an optimized design using Karnaugh map and whatever you say. So, Karnaugh map or what you can sometimes you can say that Queen-Masklansky, and you get this is the this is A B bar plus A bar B, this is actually A XOR B, okay, for the sum, and this is for the carry. So, this you can very easily generate from this table, and there are, I mean, this is the sum and this is the carry. So, what we can do, there is some techniques like Karnaugh map and Queen-Masklansky, okay, standard we have already learned in digital design, but the problem is that Queen-Masklansky and this Karnaugh map work if the number of inputs are less. So, in case of VLSI the number of inputs can be in thousands. So, how will you do that? How CAD tools can be developed that can automatically minimize circuits when the input is thousands or even more than that. So, that we will be learning in the design module of the course. Okay. And so, this is about the from what you can say that from the RTL design. So, we have gone to the logic design, that is actually called logic synthesis, but again there should be an equivalence preserving step, but this should be an equivalence preserving step. So, what do you mean by equivalence preserving? That we had some adder description. So, here some adder description was there. So, what is say that it says it will do A plus B equal to C, this sum and carry, and it will also do C plus D. So, that is the basic job of the adder. Now, you have to verify whether it is really doable by this circuit, because this circuit we have got after logic synthesis. So, the same adder in the block level we say that A plus B or C plus D is now converted into something like this. So, you have to formally say that, or you have to somehow say that both of them are equivalent. So, for that we have to actually do something like called formal verification. So, in case of adder it was only 2 bits, so you could try 0 0 0 1 1 0 and 1 1, but if it is 1000 input case type, then you are at a big problem. So, in this case what you have to do? You have to do that formally. So, there can be some type of that we will be learning in our formal verification module. So, what we will do is that we will model the circuit in some formal models, and then we will try to verify mathematically whether everything is proper or not. So, what are some important models to capture the RTL design or the architectural design? There is something called control data flow graph and something is called the finite state machine. Like for example, if you look at this, so what is the data flow? So, what you do, you read A, read B and write out 1, read C, read D and write out 2, and there is a control. So, if 0, so this is going to happen, and if 1, then C plus D is going to happen. So, this is actually the mathematical model of your whole circuit. This whole circuit is being mathematically modeled over here. This circuit is mathematically modeled via control and data path flow here. So, this is the case. Now, what it says that there is a finite state machine for the controller. So, in stage 0, it is 0 and 0. So, it is activating this one, and in the second stage it goes here and the activation is 1. So, this is the finite state machine model of the controller. Now, we will see in the formal verification module how can you use these models to verify that what we required in design. So, that was the requirement of the design was this one A plus B, C plus D, this was our requirement of the design, and this is being possible by this circuit. So, this can be verified by this model. So, how we do the verification and the mathematical procedures are there, that we will be learning in the what you call our verification class. And from this for the adder, for the registers and all, so we have to get something called this logic gate level diagram. So, again we have to mathematically verify that this stuff and what you can say this this model are mathematically equivalent. So, again we have to make a formal model for the gate level circuit, and then you have to see that whether they are equivalent to the adder, resistor should be equivalent to the resistor and mask should be equivalent to mask. So, in this case what we have done, we have taken the equation like out 1 equal to A plus B and out 2 equal to C plus D, and we want to implement in this one. So, this one we have converted it into a formal model like this, and we will verify. Next stage what we have done, we will take this adder, resistors and all, and for the adder we have got a circuit like this by using some kind of optimization technique like Karnaugh member Quinn-McLean's. Now, you have to verify that this one, this gate, we have to make a formal model for this, and you have to show that it is equivalent to this functionality. So, this is the next stage, and then what we do is that then we go for the back end. So, in back end already I told you. So, what do? You actually make an idea where you will place the gates, which is called the floor plan. That is the overall plan, that here I will put the AND gates, here I will put the adders, here I will put the multiplexers, here I will put the memory block and so forth. That is actually called the broad level placement of your gates in the die. That is called floor plan. And placement and routing, what we do? Now, we think about individual gates, in which row of the die you will put and how you do make the connection. That is called placement and routing. So, once you have done this, again you have to verify that the placement and routing what I have done is equivalent to this one. So, in that case what we do, we again abstract out what we have laid out in the circuit, and then we try to again go for a formal equivalence check with this one in verification. But in this course we will not be looking into the back end design, so we will not talk more about back end. So, next stage, once all these things are done, fabrication has been done. So, what do? You sell off your circuit, send the circuit for manufacturing, and at the same time we can also go for test planning. So, now what is test planning and why it is required? So, already I told you that in test design manufacturing nowadays, what we do? We are actually putting large number of transistors in one chip. So, there can be physical defects when we are fabricating. So, what you have to do? You have to test them by applying some test pattern. When the circuit has been fabricated, you apply some test patterns and you see whether they are proper or not. So, again this is the curse of dimensionality problem is there. So, if you have 2 to the power n pins, then you have to apply 2 to the power n test vectors, and now you have to go for all the chips, you have to do this. So, there is a big problem over here. So, it is an even more big problem than verification, because verification has to be done for only one design and testing has to be done for all the chips manufactured. So, somehow what is testing what it will do? So, if there are n inputs in the circuit and you are trying for all 2 to the power n vectors, that is actually called the functional testing of the circuit. This is actually called the functional testing. So, this is called exhaustive is functional testing, called exhaustive, that is n inputs are there and you are giving all 2 to the power n possibilities to test the circuit. So, it is called exhaustive functional test, which is prohibitive, as you see. If n is about more than 1000, it is impossible to do that. So, what is the test flow of the project or course or in VLSI flow does? It tells you which subset of 2 to the power n you have to apply, so that you can be your time will be less, as well as you can be really very confident to do that. So, you will see in the test module of the course that there is something called structural testing, in which case what we do is that we do not think anything about the functionality of the circuit, rather we treat the circuit as structural level. Like let me explain in the circuit. So, here is a sum and is a carry. So, in structural testing, in functional testing you will have to apply A and B are there. So, you have to apply 2 to the power 2, all the 4 patterns you have to apply and test. But in case of structural testing, we do not think this circuit as an adder or a subtractor. There is a structural connectivity of nets, and there is next is something called a fault model. So, we will assume that Stacked fault model is a very well known fault model. So, what is a Stacked fault model? Stacked fault model assumes that this line can have a Stacked 0 or Stacked 1. Stacked 0 and Stacked 1 means this line, if it is Stacked 0, so this line is always at 0. Even if you apply a 1 over here, it will not go to 1, it will remain as 0. And for Stacked 1, so this line is always at 1. If you have given a 0 over here, it will not go down to 0. That is the Stacked 1 and Stacked 0 fault model. So, what the structural testing will do? You have to apply some test vectors here, so that you can be assured that there is no Stacked 1 0 fault here, no Stacked 0 1 fault here, and for all the nets. So, in this circuit, how many lines are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So, you can study that there are 12 line nets in this circuit. So, 12 into 2. So, there will be 24 Stacked 0 and Stacked 1 faults. So, 12 lines means 12 Stacked 0 and 12 Stacked 1 conditions, because Stacked 1 and Stacked 0 you have to see for all the lines. Here you have to verify there is no Stacked 0 fault, here you have to verify there is no Stacked 1 fault, similarly for one at a time. So, you need not take all combinations, like you need not take Stacked 0 here, Stacked 0 here. No, you take one case at a time, that this is Stacked 0, you have to verify that there is no Stacked 0 fault. There is Stacked 0 here, no Stacked 0 fault. Similarly, you have to take all the Stacked faults one at a time in all the nets of the circuit. Then what you do? Then you find out test vectors which can actually assure that there is no stuck at 0 fault here or no stuck at 1 fault here, something like that. So in this case there are 12 lines, so 24 cases will be there, which will tell you that there are 24 cases of faults in this. Okay. So if you are thinking about the general fault case, so there can be n number of defects, like this line can be short, this line can be short with this one, this OR gate may be converted into an AND gate because of fabrication defect, so this NOT gate may becomes an inverter. So there can be infinite number of faults possible in this circuit. So if you want to test for all, then you will go mad in time, you cannot do that. So the structural testing tells you that don't think about the functionality and don't think about all kind of defects that may take place, only think that some particular type of faults are there, that is stuck at fault, that is actually called the fault model. There are different type of fault model, stuck at, bridging and all, so that will be elaborated in the module when we go to the testing module. For the time being, let us assume that only stuck at fault model is there, which can give you a very good assurance that the circuit does not have any fault. So what you have to verify that none of the lines has any stuck at 0 fault. So how can you verify that? You have to find out a test pattern which can assure that there is no stuck at 0 fault here or no stuck at 1 fault here, and you have to repeat it for all the lines one at a time. So let me explain with an example. So let us assume that there is a stuck at 0 fault here. Somehow you have to verify that there is no stuck at 0 fault here. So something like that, stuck at 0 means let us assume that there is electric bulb in your room and it does not become glow, it does not glow, so always it is 0. So how can you test that the bulb is not fused? You have to put it 1, that is you have to give a reverse value. If you stuck at 0, you have to apply try to put a 1. So how can you put a 1 over here? You have to put a 1 over the AND gate and you have to put a 0 with the inverter, so it will be 1. So 1 and a 1, so you should get a 1. But it may happen that because of the fault, it may remain a 0. So 1, 0 if fault is there, else it will be 1. Similarly, it is a OR gate, so you can put A equal to 1, so you will get the answer 0, 0, so the answer is a 0 over here. So sum is, this is the sum. In structural testing, you do not think about the functionality. So if the fault is not there, so what will be happen? 1 or 0, the answer will be 1. But if the fault is there, so it will be 0 or 0, the answer will be 0. So you apply the pattern 1 0 1 0, and if you get the answer 1, then you can be assured that this stuck at 0 fault is not at all present. But if you get a 0, then you can know that a stuck at 0 fault is there and the chip has a defect. So now, so in this case, how many faults were there? We see that there are 24 faults. 24 faults are there. So 24 patterns will be required to test your circuit. Okay, but this is a small circuit. So if you want to go for a functional model, so there is A, B, there are only 2 models. So 2 to the power 4, only 4 patterns are there. So and if you are going for structural testing, so you have to apply 24 patterns, 1 for each fault. But actually this is not the fact. So when we will see a large circuit, as we will go in our test module, we will find that the condition will actually reverse. The number of nets in a circuit is n. Okay. So if the number of nets in a circuit is n, then how many faults can be possible? 2n. Okay. And in a practical circuit, if there are 100 inputs, okay, so you can think that there is around 10,000 lines in this circuit. So that is an approximate number. Okay, 100 inputs in a circuit, so there will be around 10,000 lines. So how many faults are there? Stuck at 0 and stuck at 1, 2,000 faults are there. Okay, so sorry, 2,000 faults are there. 1,000 line, 2,000 faults. Then how many inputs you have to give? So you require some 2,000 input patterns to verify that none of the stuck at 0 and stuck at 1 faults are there. In this case, you have seen that for stuck at 0 fault, you require this pattern to verify that there is no stuck at fault. But how many input patterns you want to require if you are going to go for exhaustive functional testing? It will be 2 to the power 100, which is an exponential problem and it cannot be solved. So that is what is actually called structural testing. So what do we do in structural testing? We say that we do forget about the functionality of the circuit. We take a fault model, stuck at 0, stuck at 1 is a very well accepted fault model. Then we apply patterns or find out patterns like this. So how many, if there are n lines in the circuit, 2 n patterns will be found at max, so that which can assure you that none of the lines in the circuit has a stuck at 0 and stuck at 1 fault. And it is established experimentally that this is equivalent to, in level of confidence equivalent to 2 to the power n, 2 to the power number of inputs. If you apply to this circuit, that confidence you get. So if you have n inputs in the circuit, you apply 2 to the power I, if there are I inputs in the circuit, you apply 2 to the power I input vectors and some confidence you get. So that confidence is almost equivalent to 2n test patterns if you apply for testing the stuck at fault. So structural testing is a widely accepted test fault model and test methodology. So what we will see in the test module of the course, we will see how you can, given a circuit, how you can find out which are the very important vectors to test the circuit. So which are the important vectors? This 2 to the power I is actually the superset of nothing but 2n. So, 2n is a very small amount of test patterns compared to 2 to the power I. But how can you determine this 2n or a subset of this? That is, you have to apply, you have to give faults at all the points in the circuit, and then you have to find out automatically by using tools which pattern you have to apply. And you will also surprisingly see that this 2n will actually come to a very less level, even hundreds or less, because many of the faults, structural faults are equivalent, and same pattern can detect multiple number of faults. So, you will be very much surprised that 2n will eventually come to very less than n by k. It will be a very small fraction of n because of fault collapsing and equivalence of fault, that is one test vector can test multiple number of test vectors. So, we will find out from 2 to the power I will come to n by k level. So, in testing module what we will do, we will take a circuit, automatically we will apply the stacked faults at all the points in the circuit or whatever fault model you take, and automatically the CAD tool will tell you which is the test vectors to be applied when the circuit is to be tested. So, this is called the test planning of the circuit. So, now once the test plan has been done, circuit is manufactured, verified, and it is given to for manufacturing, and when it is fabricated it will come back to you. So, whatever test plan you have done, so in this case test plan here means that you have found out the test vectors. So, whatever test plan or whatever test vectors you have already pre-computed and kept in your memory. So, when the chip will be fabricated and brought back to you, so you will apply those test patterns, which is now 2n or more precisely n by k, you apply to all the chips, and if you find that somehow there is a fault found in the chip, so that you will throw out, and all other chips you will sell off to your customer. So, this is actually comprises the whole CAD tool development process for VLSI design, verification and test for digital circuits. So, what we will learn, this course will have 3 basic modules. So, first will be the design module. So, we have already seen the design flow. Next next lectures will be on high level synthesis. Following that we will have scheduling, allocation and binding for high level synthesis. Then we will have logic optimization and synthesis, that is actually logic synthesis, how you from the RTA level how you can go to gate level stuff, that we will see. So, that will complete your design part. Next we will have verification part, that is how automatic tools can be developed to verify each translation or when you are going from one version of the circuit to other, like from gate level to RTA, from RTA level to gate level, or from specification level to RTA level, how can you verify them. So, in that verification part we learn binary decision diagram, temporal logic and model checking. And finally, when you will come to testing, so we will have introduction to testing, so from some fault simulation, how you can generate test pattern for combinational circuit, how can you generate test pattern for sequential circuit, how can you test memories. So, we will have a very broad level discussion or in-depth discussion of how you can go for good test planning. Only one module which we will not be covering in this course will be actually layout part, the back end part, how CAD tools can be developed for the back end part, that we will not be able to go in depth in the course. So, whenever we will get time, so we will speak something about that, because the course mainly covers 3 major topics in the front end part of digital design into one course and in a nutshell. So, that is what will be our tentative plan. So, thank you for the first lecture, for attending the first lecture, and in the next class we will start going into depth in CAD tools for high level synthesis. Thank you.